All right, so you can go ahead and set up your notebook page. Make sure you pause the video if you need to. Now, exponential functions, we did talk about a little bit in chapter 2. We know that their equation is y equals a times b to the x, where b represents the base, and a represents our initial or our start value. And every exponential function has an asymptote, which is the horizontal line y equals 0. Number 56, since exponential functions are so useful for modeling situations in the world, the inverse of an exponential function is also important. We're going to use y equals 3 to the x as an example, and even though we might not be able to write the inverse as a y equals equation, we still know a lot about it. So before I create a table of the inverse, I like to make a table of the original, always making sure I do some negatives and some positives. I know that 3 to the 0 power of anything to the 0 power is always going to be equal to 1. 3 to the first is 3, 3 squared is 9, 3 cubed is 27. And then when I'm working the other way, I've got 3 to the negative first, which is 1 over 3. 3 to the negative second is 1 over 9. 3 to the negative third is 1 over 27. And so now when I'm making my table of the inverse, it's super easy. All I need to do is flip my x's and y's. Next, we're going to graph the inverse. So those are all my red points. If you wanted, you could graph the original as well, just for that visual comparison. But we do know how inverses and original graphs are related because they are symmetrical across the line y equals x. And I'm just going to approximate to the best of my ability for what these fractional or decimal x values would be. Now, because we had an asymptote in our original, we are going to have an asymptote in our inverse. Our asymptote originally was at y equals 0, so when I flip my x's and y's, my asymptote is now at x equals 0. And then writing the equation for the inverse, we know that it's just flipping our x's and y's. Right now we can't do anything else or anything additional in order to isolate that y. So we'll just use this equation. If the input for the inverse is 81, what is the output? So now the input, due to the way our equation is set up, that input is still going to be that x value, which I know seems confusing because you're used to that answer being our output or our y value, but that x value is still our input. And we know that when I have an exponent, exponents just represent repeated multiplication. So I'm just going to see how many 3's it takes multiplied together in order to get to that 81. So it looks like I've got 1, 2, 3, and 4. which means 3 to the 4th power does get me 81. So my output, because it's my y value, is going to equal 4. Now, if we were to make a new equation g of x that represents this function, just exactly what we did in C and D, how would you describe the outcome, which again is that y value? So the way that I make sense of it in my head, the outcome is the number of times the base which we know was that 3 is multiplied. And by multiplied, I mean by itself, right? So 3 times 3 times 3, and it's how many times that is in order to get that, that input, which is the 81.